through it.
Yeah, I'm saying.
The one thing I forgot to give you guys was the Tableau assignment.
I thought there
didn't-
was supposed to be
I
something.
didn't give you, I completely, I looked at it, I'm like, I didn't give them the Tableau assignment. And that was kind of the whole fun of a lot of this stuff was generating the, well, not generating the Tableau, but, yeah, my mistake. Any questions? Was it difficult?
It was a little frustrating.
It's a little frustrating. Your email was really on point to what we're doing today. So you noticed that nothing was coming out significant, right? So when we tested
The hypothesis.
the hypothesis testing, so when we were testing the hypothesis, we tested two things. One, were they equal to each other? And the answer was yes. And then two, were they all equal to 0? And the answer again was yes. So nothing's coming out significant. And that would be kind of depressing if it was true, because it means that that promotion is having no effect. And it turns out that we were using the wrong methodology. So multinomial logit is really good, it's really powerful, but there are some subtle assumptions that we need to talk about today that we may not be satisfying, and that might be the reason why things weren't coming out statistically significant. So these are kind of technical assumptions, but we'll get them in a bit. One of them has to do with the types of data in the data sets. This is something called case versus alternative specific data. So case-specific data contains variables and information on how individual characteristics affect behavior. So these are things like, and the most common case-specific variables are demographic variables. So things like age, income, gender, other things that would be included in a Nielsen or IRI data set would be family size. Income would be in there. So, and that's the only other one that I think that would be missing. Family size would be in there. Obviously, if you've got a bigger family, you're buying more crackers. And other stuff. So these are specifically called case-specific variables. These vary across cases, in other words, across individuals, but they don't vary across alternatives. And we'll see what the heck that means. Alternative-specific variables, on the other hand, are variables that take on different values across the alternatives. All right, what the heck does that mean? Did we talk about this? Modeling to get to work, are you taking car, bus, or train? And in this case, each alternative would have a different cost for each family. So depending on where you live, depending on what kind of city you live in, whether you got a lot of traffic, whether you got a little traffic. If you live in San Francisco, travel time is different than if you live in Sonoma County. So each alternative has a different value based on, or each alternative has a different value. Not everybody's facing the same price, for example. So yeah, think of these as the cost of each alternative differ for different travelers. This is another example that I pulled from a textbook with Ismail. Suppose you're trying to model what kind of car people buy. Apparently these people modeled it based on the number of dealerships in the city that the people live in. But not all cities have the same number of dealerships, so if I want a Honda, I might have to go further than if I was getting a domestic car. In our particular case, price and promotion is going to differ for each alternative. Why? Because people shop at different times and in different stores. So remember how this data works. It's not everybody going to the same store and facing the same prices. It's literally every family shopping wherever they go. They come home, they scan their stuff, And depending on where they shopped, they're going to face a different price for the same product. Depending on when they shopped and where they shopped, they're going to face a different promotional aspect. They might be on display at Safeway, but no promotion at Kroger's, and it might be on feature at Rayleigh's. So alternative specific data occurs when essentially it's going to be mostly prices, but the prices differ across each alternative for each person. Yeah, so think of the costs or the prices are different for different shoppers. And I think in all three of these cases, you can think of these as prices. Travel time is an opportunity cost of being in the car. That's going to differ if you live in San Francisco. Going 1 mile is going to differ than going Sonoma County 1 mile. By the way, the other day I was looking at my GPS meeting. I was 1.4 miles away. It took me 25 minutes in San Francisco to get 1.4 miles. It was insane. Yet I can go to Hillsburg in 25 minutes if I wanted to. So think of these as costs. Travel time is a cost. The number of car dealerships is a cost, because if I don't have a car dealership in my locality, I got to travel further. And then of course, price and promotion are going to be costs also. So demographic, the easiest way I remember these things, and these technical definitions are always difficult. The easiest way I remember these are case-specific variables are going to be demographic characteristics. Alternative specific variables are things like price and cost and promotion. Now for most of us, in most of these kinds of data sets, these panel data sets, these household panel data sets, the whole point of these household panel data sets is to get the case-specific data, to get the demographic characteristics of the family, the income, the family size, and all those things, so that we can get a more accurate model of consumer behavior. So you're almost always going to have case-specific data when you analyze household panel data. We don't have it in this case because I had to get rid of it, so I wasn't allowed to use it. It's that simple. A lot of this, like I said, a lot of this data is really, really expensive, and sometimes I'm told I can't use the data, so I don't use it. Sometimes I'm told I got to destroy the data, so I destroy it.
Do they not know how computers work?
What's that?
Do they not know how computers work?
Yeah, but you sign a non-disclosure agreement when you do these consulting jobs, and but if the firm doesn't say anything, then sometimes I'll ask them, do you mind if I use this data, in classes? Sometimes I won't ask, but sometimes I will ask if I think that maybe they overlook the fact that I might use it. I don't like to brag about using it, but I will sometimes ask. In some of these cases, they ask you, okay, but you have to anonymize it. So you have to get rid of some of the, in this case, the demographic characteristics. So we got the prices and those things, but we don't have the demographic characteristics, which is really the unique thing of these household panel data sets from both Nielsen and IRI. Okay, well, why does this matter? Well, because depending on the type of data, is going to dictate what kind of methodology you should use. So, and then how the data is going to be set up. So with alternative specific data, usually you have one row of data is going to represent one case. So you're going to have as many, let's see, alternative specific data is you're going to have as many values for a variable as there are alternatives. And that's going to be different than for case-specific data. Let's see if we can look at this. Okay, so this is data set up in a alternative specific data. In the data we have, each row of data represents a purchase. It represents a specific household's purchase. In alternative specific data, you're going to have as many observations for each household as you have alternatives. So in this case, we have 3 alternatives: train, bus, and car. Modes of transportation. And so each observation, each household observation is going to have 3 actual observations. So again, as many observations as you have alternatives for each individual purchase behavior. Does that make sense? It's difficult to say. Now, the way our data looks is not like this. Our data is literally, right, here's a household ID, and then here is our choice variable, and then here was a price, promotions and quantities and all that stuff. And this was one observation. The next observation was a separate ID. The next observation was a separate ID. So if we had 3 observations, those are 3 different purchases. This is 6 observations, but it's only 2 different purchases. This is for the first household ID, and this is for the second household ID. So in essence, your data set's going to go from Y to a lot longer. Your data sets are going to, in this case, increase by a factor of 3, because you're going to have 3 observations for each instead of just 1. And we have to figure out how to fix that. I think we've already reshaped, but we'll reshape again. So we can see how the data is set up. Time is, where is time is our alternative specific variable, as is in vehicle class, which is what INVC stands for. Again, tell you, time is alternative specific. In vehicle class is alternative specific. Train and bus are going to be dummies for those individual alternatives. So what we have to get used to is seeing, if we have alternative specific data, what we have to get used to is seeing data in this format, in this, again, what's called a long format. We got these 2 dummies here, which are the same as these 2 dummies. And our choice variable in our multinomial logit model, our choice variable was the number, was crackers. It was 1, 2, 3, or 4. Keebler, Nabisco, Sunshine, and private label. Here our choice variable is a binary. It's 0, 1. And you can see that it's, so the second person drove by car, as did the first person. So the data is set up set up differently. The choice independent variable, the choice variable is set up differently. The data is set up differently, and we're going to use different methodologies to analyze data that is in alternative specific format. Technically, the multinomial choice model is for case-specific data only. But notice that none of the variables in our cracker data set are case-specific variables. They're all alternative-specific data. So technically, we were doing everything wrong. We weren't doing anything wrong. Technically, we were using the wrong methodology. And the reason it makes a difference is because it really has to do with the error terms and how the error terms are constructed. So our results may not be necessarily wrong. Where things end up is in the error terms. And why is that important? In Stata, right, if we're doing a t-test, the t-statistic is basically your coefficient over your standard error. So if our standard errors are wrong, we get greater standard errors, then our t-statistics are going to be smaller, which means nothing's going to appear to be statistically significant. That's the problem. We're using a methodology that is, more appropriate for, case-specific data when our variables are alternative specific variables. Why would I have you do that, knowing that it's the wrong one? Because as we'll find out, because of margins and margins plots. Multinomial logit still works with margins and margins plots. These new methods we're going to use today don't. So, remember the whole point of this class is to create visuals that are going to make these models more understandable. Again, using multinomial logit doesn't mean our results were wrong, it just means that they may not be, our standard errors are not as accurate, and hence our T and Z statistics are not going to be as accurate. But it doesn't mean we're necessarily going to get wrong results. And you know, I hate to do this, especially on tape, is what I do. What I'll do is I'll use the visuals from the multinomial logit model because they're so much nicer. And I can construct a Tableau's dashboard. But when I refer to the actual numbers and the analytics, we'll refer to the correct methods. So, is that cheating? No. Let's just say no and move on. All right, so let's move on to the next slide. Okay, so the choice is binary and not the multinomial like it is in the multinomial logit model. So what are the models that are available for us for alternative specific variables? The first one is called the conditional logit model. And this is designed specifically for alternative specific characteristics. And yeah, here's all the math and all that stuff. And the data's got to be in the right format. We'll get to that. Each case has an ID. Again, with 3 alternatives, you get 3 observations per ID. Let's see, these are all alternative specific variables, so they're going to vary. And again, we can see that travel time is different for ID 1 than it is for, actually they're the same. Why are they the same? I'm sorry, this is in-vehicle cost. Yeah, travel time is different. In-vehicle cost is the same for these. They shouldn't be. All right, so here is an output for our conditional logit model. And actually saying conditional logit with alternative specific data is redundant because conditional logit models only work with alternative specific data. How do we interpret this? So we could have run this with our cracker data and we would have been 100% fine. How do you interpret these? Well, they're still logit models and they're still log of relative odds ratios and we still have all that stuff. Positive coefficient means your as the variable increases for one category, then that category is going to be chosen more than the other. Vice versa, a negative coefficient means that as the independent variable increases for one category, then that category is going to be chosen less and the other categories are going to be chosen more. So all these tell us are that as travel time increases, you're going to tend to pick one category less and the other more. Same with in-vehicle costs. And the dummies, the fixed effects or the dummies just tell us that the odds of choosing, not the odds, the log of the odds, it's negative, so we're less likely to choose bus relative to train, and we're less likely to choose car relative to train for this particular data set. And again, those would change if we change the base. So again, conditional logit, we use it only for alternative specific data. It's not set up to handle case specific data. Something that handles both of them is, let's see, kind of compare the multinomial logit model that we used and the conditional logit model. They're actually mathematically equivalent. Estimation is the same way through likelihood. You get the same results if you run them both with only case-specific variables. Interpretation is the same, all that stuff. So again, what's going to be affected is the standard error. And remember, the standard error is, so we estimate coefficients, and it comes from a distribution of possible coefficients. So here's one of our betas. The standard error is the standard deviation of the sampling distribution. So if our standard errors get bigger, it just means that this distribution gets fatter, meaning that more extreme observations are more likely. We're more likely to get results that are overestimated or underestimated. Now, there's no bias in that we're consistently overestimating or underestimating. It just means that there's more variation in our possible outcomes. Hence, we're not as confident in our estimates, which results in lower t's and higher p-values. So that's the problem with these. Okay, so we don't need to do that. The more flexible model, and the model I like to use more often, is something called McFadden's choice model. This handles both alternative and case-specific variables, and it's, what is that? We're just kind of adding the multinomial logit with the conditional logit, and we get this mixed conditional logit, or what I refer to as, or it's often referred to as the McFadden's choice model. Here's the outcome from McFadden's choice model. Let's see, what do we have here? So this is a different data set. We still have the alternative specific variables, which are time and in-vehicle cost. Let's see what we have. Alternative specific variables. Again, same interpretation. They're negative like they were before. And for the case-specific variables, we have, again, demographic characteristics, which are household income and party size. And party size is the size of the party travel. And this is the more flexible model. Now, in our Cracker data set, we only have alternative specific data, so we don't have the nice case-specific demographic variables, so we can get away with using the conditional logit. The McFadden choice model reduces to the conditional logit if you only have alternative specific variables, so it really doesn't matter. I just like using the more general case, which is McFadden's choice model. So one of the problems was we're using a model designed for a different type of data set, data structure. Actually, data set's fine, because the variables contained in the data set. The other problem is something called, this is a mouthful, the independence of irrelevant alternatives. And again, this is one of those wacky econometric assumptions. What does it mean? Let's see. Let's get to the example. Here it goes. It means that adding or deleting alternatives does not affect the odds of the remaining alternatives. So McFadden came up with this red bus, blue bus example. So suppose we have three ways of getting to work: by car, by blue bus, and by red bus. And the blue buses and the red buses are identical in every way, shape, or form except the color. One's blue, one's red. Let's just assume that each is equally likely. So you have a 1/3 chance of taking a car, a red bus, or a blue bus. Now, what the independence of irrelevant alternatives says is that, and we can see this from our relative risk ratio. So the relative risk ratio of car relative to blue bus is 0.33. They're both 1/3, so the relative risk ratio is 1. We're equally likely to take car as we are blue bus. The relative risk ratio for car and red bus, they're both 0.33, so again, we're equally likely to take car versus red bus. Now, let's assume we paint all the red buses blue, so that now we only have two choices. You only have red buses, you only have a car and a blue bus. If the independence of irrelevant alternative assumption holds, then the probability of a blue bus should be 50% and the probability of taking a car should be 50%, and hence we would have the same relative risk ratio. Does that make sense? So we had three alternatives: car, red bus, blue bus. If we painted the red buses blue, would our probability of taking car go up to 50% and bus go up to 50%? Would we add those? Wouldn't it be more likely that we would just add the probabilities of the two buses because they're the same? And hence our relative risk ratio would switch to 1/2. So if that's true, then we violate the independence of irrelevant alternatives, and we shouldn't be using the multinomial logit model. An easier way to remember this, if you don't like the red bus and blue bus example, is that if these are substitutes, if any of the categories can serve as substitutes, then you're violating the independence of irrelevant alternatives. Now, so we ask the question, can red buses and blue buses serve as substitutes for each other? Probably, exactly. If you have two categories that can serve as substitutes, we're violating the independence of irrelevant alternatives, and we probably shouldn't be using a model that assumes that the independence of irrelevant alternatives holds, which the multinomial model does. It assumes that I holds. So for two reasons, we probably shouldn't have been using our multinomial logit model. Again, this has to do with the error terms, the correlation of the error terms across our substitutes. Again, they can serve as a substitute. Let's see. Multinomial logit and probit models, as well as the conditional logit model, all make the same assumption of independence of irrelevant alternatives. So we need some new models. A couple of examples. So let's say we got three options for drinks: coffee, Gatorade, and Coke. Is the independence of irrelevant assumptions met? I know what you're going to say. Probably, because it says that there. I need to change the PowerPoint and not give it away. Think about it. I'm thirsty, but I'm thirsty for different reasons. I wake up in the morning, I gotta have my Gatorade. I gotta have my cup of coffee. I just finished a workout, I wanna have my Gatorade, and I have some rum, so I gotta have some Coke. I'm not thinking about these as substitutes. If I have rum, I don't, well, I guess you could put it in your coffee too. But if I'm waking up in the morning, I'm probably not thinking about having a Coke or Gatorade. And if I just finished a workout, I'm probably not thinking about Coke and coffee. And if I have rum, let's just pretend I'm not going to put it in my coffee or my Gatorade. So in this case, the independence of irrelevant alternatives is probably going to be met. This makes sense for this to hold. If we added another category, coffee, Gatorade, and Coke and Pepsi. Again, coffee, Gatorade are probably not substitutes, but Coke and Pepsi are clearly substitutes. So this would be a violation of IIA. Yeah. One from politics, Bush versus Gore. If the independence of irrelevant alternatives is met, then the relative odds of voting for Gore and Bush should not change if an independent candidate like Ralph Nader is added or removed from the ballot. So remember that IIA holds that if we add or remove another alternative, that the relative odds ratio should stay the same. In this case, we know that, or we could assume that if Nader is removed, voters would choose Bush and Gore in similar patterns to the rest of the sample. But we know that's not true. If Nader was removed, those voters would probably go to Gore, and yeah, would probably go to Gore, and that would violate the independence of irrelevant alternatives assumption. All right. It's a strong assumption. It's probably going to fail if these alternatives are going to be substitutes. So, whoops. McFadden himself says, look, it's a pretty strong assumption. Most of the time we have substitutes, like in our crackers. They're all, think of them as substitutes for each other. So it's probably not going to hold. Given that, we have these tests of the independence of irrelevant alternatives, and let's just kind of burn through this.
No, that equation looks nice.
Yeah, the equation's awesome. But essentially what they do is they take one of the categories, remove it. So they take your multinomial logic, they run the full model, then they take one of the categories and they remove it, and then they basically compare you can see here, they compare the coefficients from the restricted model, where one of the categories has been removed, with the unrestricted model, where all the categories are in there, and they want to see if those coefficients differ. They also look at the variance between the two categories and see if those differ when we remove one of the categories. I'm sorry, the variance between the two regressions, and see if they differ when we remove one of the categories. If they differ significantly, then we'll get a statistically significant Hausman and McFadden statistic.